Assalamu alaikum. In the last lecture we talked about improving steady state response characteristics, and in today's lecture we shall talk about improving the transient response characteristics. You remember that transient characteristics as well as stability, that is determined by the location of closed loop poles. So from the location of from the design specifications, you determine the location of closed loop poles. If these closed loop poles lie on the root locus, then simply we can change the gain to achieve the desired transient specifications, and we have already talked about that procedure. If these desired closed loop poles lie on root locus, then gain adjustment. If these desired closed loop poles do not lie on the root locus, then we have to somehow reshape the root locus so that it passes through the desired closed loop poles. So how to reshape the root locus? To reshape a root locus, we can, for example, use two types of controllers. One is PD controller, and the second one is called lead compensator. The transfer function of PD controller is given by Kc s plus Zc. So if we just expand it, we have Kc s plus Kc Zc. That is the proportional action plus derivative action. So that is the reason of its name, proportional plus derivative controller, PD controller. The transfer function of lead compensator looks quite similar to that of lag compensator. It is given by this transfer function is quite similar to that of a lag compensator. In the case of lag compensator, we did not want to change the shape of root locus. That is, we were satisfied with the transient characteristics and we did not want to modify the root locus. Therefore, Zc and Pc was very close to each other. Due to that, the angle contribution due to this numerator, that is due to 0, was the same as the angle contribution due to the pole, and therefore net angle contribution in the case of lag compensator was almost 0, and hence the shape of the root locus was preserved. Here we want to reshape the root locus. That is, this has to contribute some angle. We want to change the shape of the root locus. That is, this has to provide some angle contribution, and therefore Zc and Pc in case of lead compensator are not very close to each other. This is the only difference. This is the difference between lead compensator and lag compensator. So design procedure for PD controller and lead compensator is quite similar. So we start with the discussion of design of lead compensator. For that purpose, let's consider a particular system, again unity feedback system. So to demonstrate the procedure for the design of lead compensator to improve transient response, we consider this system. G of s is given by this transfer function, and we want to design a compensator such that the closed loop system exhibits these transient characteristics. That is, we want an overshoot of 60% and settling time of 2 seconds. From these design requirements, we find the location of desired closed loop poles. So from overshoot requirement, zeta can be easily computed. You remember that overshoot is equal to e raised to the power minus zeta pi over 1 minus zeta square whole square root, and for percent overshoot we multiply it by 100. From this requirement, overshoot is given and we can easily compute zeta. This comes out to be equal to 0.5. And from the settling time requirement, we know that Ts is equal to 4 over zeta omega n. So settling time, required settling time is 2 seconds. Zeta has already been computed. We can compute omega n, and omega n comes out to be equal to 4 radians per second. Omega n is 4. So therefore the location of desired closed loop poles S1, 2, that is minus zeta omega n plus minus omega n into 1 minus zeta square, here is j. And this desired location comes out to be equal to minus 2 plus minus j 2 square root of 3. So to achieve these desired specification, closed loop poles of the system should be located at this point. So let's first sketch the root locus for the original system. Root locus can be easily sketched. We have S-plane, and one pole is at origin, another pole is at S equal to minus 2. So the root locus, this is root locus for the system, and the location of desired closed loop poles, we have a pole at S equal to minus 2 plus j. So S equal to minus 2 plus j 2 multiplied by, so one desired closed loop pole is at this location, the second one is its complex conjugate. We can see that the root locus is not passing through these desired closed loop poles, that is, the angle condition is not satisfied for this point. We can verify that angle condition is not satisfied for these particular points, that is, the angle of g of s at s equal to these desired points, that is basically equal to 4 over s1, which is this s1 angle of this one plus angle of 4 does not contribute anything to the angle, so I just omitted 1 over s1 plus 2. Instead of s, we have simply substituted s1, and since these two terms, this term and this term, these are being multiplied, therefore their angles are added. That is angle of this thing s1 minus angle of s1 plus 2. This angle, what is this angle? Angle s1. S1 is the angle of this vector, and s1 plus 2 is this vector from here to here. So you can verify that this total angle is not equal to 180 degree. That is why root locus is not passing through these points. What we need to do is we want to reshape this root locus so that root locus passes through these points. That is, angle condition is satisfied for these points. For that purpose, what we do is we place a 0 of the compensator and a pole of the compensator, and then there will be an angle contribution due to the 0 and angle contribution due to pole of the compensator, and the location of this 0 and pole will be selected such that angle condition is satisfied for this particular point. So let's see how is that done. So we have the angle due to this 0, let's call it theta 0, and this angle theta pole. We need to determine these angles, theta 0 minus theta pole, the angle due to 0, angle due to pole. Angles due to zeros are taken positive, angles due to poles are taken to be negative, and let's call this angle theta 1. Let's call this angle theta 1 and this angle theta 2. So minus theta 1 minus theta 2, we want to make it equal to 180 degrees so that angle condition is satisfied for this particular point. So theta 0 minus theta p, what is theta 1? Theta 1 is 180 degrees minus tangent inverse of this length, which is 2 into square root of 3 divided by this length, which is 2. So that is theta 1 minus theta 2. Theta 2 is 90 degrees. So we want it to be equal to 180 degrees. This angle comes out to be equal to 60 degrees. So theta z minus theta p minus 180 degrees minus this is 60 degrees minus 90 degrees. We want it to be equal to 180 degrees, which is equal to theta z minus theta p. If I bring all these terms to the right hand side, this is positive and then negative. So this angle comes out to be equal to 30 degrees. This angle is, so the compensator has to contribute an angle of 30 degrees such that angle condition is satisfied for this point and root locus passes through this point. This is called angle deficiency. So we have computed the angle deficiency, and this angle has to be contributed by the compensator so that angle condition is satisfied for this point and root locus therefore passes through this point. So this angle deficiency can be achieved, fulfilled in several different ways, and there are several different choices. For example, we can place the 0 such that this contributes an angle of 60 degrees and place the pole such that it contributes an angle of 30 degrees so that this difference becomes equal to 30 degrees. So for example, this is one choice. This is not the only choice. For example, another choice can be, we can contribute 90 degrees by the 0 and 60 degree, for example, by the pole. So there are infinitely many choices. So let's talk about these two choices and give a comparison between these two different choices for the compensator. Once we know these angles, this location of the 0 and location of this pole can be easily determined. So let's do that. So first we talk about this choice, theta z equal to 60 degrees and theta p equal to 30 degree. For this particular choice, if this angle is 60 degree, what will be this length? We can easily compute it by using the trigonometric relationship. Otherwise, we can also see that we have already computed this angle. This angle was 60 degree, so this length is 2. And therefore this length must also be 2, that is 0 theta z equal to 60 degree. That means that this zc, 0 of the compensator, zc will be equal to 4. The 0 of the compensator will be equal to 4. This angle is 60 degrees, so this length and this length will be equal for this angle to be also equal to 60 degrees. This angle is 30 degree, so corresponding to this 30 degree length, let's determine 30 degree angle, let's determine this length. So this length, let's call it the length x. This is x. So this height, which is 2 into square root of 3 divided by this length x, that is equal to tangent of this angle, which we want to be 30 degrees, and hence x, which is this length, is equal to 2 square root of 3 divided by tangent of 30 degrees, and this comes out to be equal to 6, and hence this length is 6. So what is location of this pole from origin to here? This length is 2 and this length is 6, so total length is 8. So pole of the compensator should be located at p at s equal to 8 minus 8. Therefore, the transfer function of the compensator gc of s is equal to kc s plus 4 and s plus 8. How to determine this kc? Kc can be determined from the magnitude condition. For this point to be a closed loop pole, this magnitude condition should be satisfied, that is g of s into gc of s, absolute value at s equal to this desired point s1, that must be equal to 1. So from this magnitude condition, the value of gain can be computed. So this value comes out to be equal to, this implies that kc is equal to, I have computed it, it comes out to be equal to 6. So our first designed compensator transfer function of the compensator is given by this relation. Let's call it gc1. This is our first compensator corresponding to these angles. Let's find the transfer function of the compensator corresponding to these things. For the angle, this is the angle contributed by 0. If it is 90 degree, so location can be easily determined. To have 0 to contribute 90 degrees, 0 must be placed over here. That is ZC will be equal to 2, and pole to contribute 60 degrees, it must be at s equal to 4. Therefore, the transfer function of the compensator gc of s is equal to kc s plus 2 over s plus 4. This case kc can be again determined from the magnitude condition, that is this condition gc of s at s equal to this point, minus 2 plus j 2 square root of 3, this must be equal to 1. From this magnitude condition we can compute kc, which comes out to be equal to 4. This kc comes out to be 4. So our second designed compensator has the transfer function given by s plus 2 over s plus 4. So what is comparison of these two controllers, two compensators? One corresponding to this choice and another corresponding to another choice. What is comparison of these two compensators? Which one is better and which one is less accurate? To give a comparison of two compensators, let's see what is the situation. For the first, for the actual system, we had a pole at this location and another pole at this location, and this was a root locus which was not passing through our desired closed loop poles. With this first compensator, we had placed 0 at s equal to minus 4 and a pole at s equal to minus 8. So new root locus was like this one. This was part of root locus, this was part of root locus, and root locus starting from this pole ended up at this 0. And then root locus starting from these poles somehow modified to pass through this desired closed loop pole. So what is total number of poles in the system, closed loop poles? One closed loop pole will be at this location, second closed loop pole will be at this location, and the third one will be somewhere on this line. So basically with this compensator we have a third order system, and the relations that were utilized for the computation of overshoots and settling time, those will be less accurate because actual system is third order and these relations were obtained for a second order system. For this case of second compensator, we have this situation. we have a pole at pole of the actual system and another pole of the actual system at s equal to -2, and this was actual root locus. The desired closed loop poles were at this location. What we did is we placed 0 at this location, 0 of the compensator, and pole of the compensator at this location. So this pole and zeros are cancelled out, and new root locus will look like this one. Root locus, this pole and zeros are cancelled out, and root locus starting from this pole and from this pole pass through this closed loop, desired closed loop pole. Again, the root locus passes through this point. However, we can see that the overall system is a second order system. Therefore, the relations for overshoot and settling time will be applicable to a higher degree compared to this compensator. So as far as transient characteristics are concerned, this compensator is superior. It will give more accurate results. Let's verify these designs with the help of MATLAB and see their performance.